Yay!
Yay! All right, one more example with the fundamental charges, fundamental particles. There's sort of a neat thing we can do, and that is to figure out for something like hydrogen, just an electron orbiting a proton, how fast is it moving? There's a certain distance between the proton and electron. So knowing what that distance is, knowing the size of the hydrogen atom, we can figure out how fast the electron has to be going around. Because let's just be brave and assume that we can use Newton's laws. It's not clear that we can. You might know that that atomic particles use a different set of physical laws called quantum mechanics, but we don't know about that yet. Let's just assume we can use Newton's laws, and let's just see what happens. So there's a positive charge in the center, and then the electron is orbiting it. So let's just treat it like a little orbiting particle. We've done this before for Newton's laws. So let's say we know that here, what are the forces on the particle? Here's the electric force on the electron. And we know, and that's the only force that's acting, let's say. So in that direction, let's call that the x direction, what we do is we sum the forces together. There's only one. So this force is directed to the left, so I'm going to say that's minus. And what is the electric force? It's K times Q1, Q2. It's the same charge, just one's plus and one's minus, but I don't care. I've already determined the direction. So it's just KE squared over their separation R squared. And this is going to be equal to its mass, the electron's mass, times how it's accelerating. Well, it's going around in a circle. Right? So if it's going around in a circle, the center of the circle is to the left. So we say that that is minus MAC. Right? So this is minus KE squared over R squared is minus MV squared over R. All right. Well, those minus signs are going to go away. So it looks like now I can solve for V, how fast the electron's going. So V, let's see, what's that going to be? It's going to be, I'm going to take the square root of all that stuff, and it's going to be KE squared, and then I'm going to have a MR on the bottom. Okay, so let's put some numbers in, and let's see how fast the electron is moving. K is 9 times 10 to the 9th. E squared 1.6 times 10 to the minus 19th squared is the fundamental charge. M, that's the mass of the thing that's going around, right? That's the electron. So if you look it up, that's going to be like 9.1 times 10 to the minus 31 kilograms. Electrons are tiny little fluffs of dust. And the R, the size of the hydrogen atom, what's that radius? You can look that up, and it's 5 times 10 to the minus 11 meters. Half of an angstrom, the 20th of a nanometer. Okay. So let's see. I mean, again, I don't care what the actual answer is down to the whatever decimal point. Let's just see roughly how fast is the electron going, right? I mean, does it go 10 meters per second or 1,000 or 100,000 or 1,000,000? That's sort of what I'm after. Is it close to the speed of light? I don't know. Let's see. If it's over the speed of light, that might indicate that this certainly is not a really valid thing to do. All right. Well, first of all, if we're just trying to do about 9 and 9.1, I can cancel those out. I don't care. So 1.6 squared, 16 squared is 256. So 1.6 squared is like 2.5. Divided by 5, that's like a half. Okay, so this is going to be square root of 0.5. That's the half. Let's see. On the top, I have 10 to the 9th and 10 to the minus 19th. 10 to the minus 19th squared. What is that? 10 to the minus 38th. 10 to the 9th. 10 to the minus 29th. And then on the bottom, minus 31 and minus 11. Goodness sakes. 10 to the minus 42 on the bottom. So this is going to be about, what is that? 0.5 times 10 to the 13th. 0.5 times 10 to the 13th. Okay, if you're just estimating things, the square root of an odd power, 10 to the 13th. That's no good. That makes your stomach turn. But I can do this. Isn't this the same thing as 5 times 10 to the 12th? Sure. And look, square root of 10 to the 12th. That's easy. That's 10 to the 6th. You just divide the power in half. And then the square root of 5. What's the square root of 5? I don't know. It's a little more than 2. 2 1/4, something like that. So this is going to be about 2.25 times 10 to the 6th meters per second. So roughly this is going to be the speed of the electron. So that's a lot, right? It's 2 million meters per second, over 2 million meters per second. And, you know, 1 meter will get you many trips around the proton because this thing is tiny. But it's not the speed of light. This is still way, way less than 3 times 10 to the 8th. That's the speed of light. So it's only it's less than 1% of the speed of light. So there's, as far as we know right now, there's no reason to think that we can't do this. We can treat the electron as just a sort of a classical problem. We don't have to worry about the special relativity and or relativistic business of things going close to the speed of light. So electrons orbiting the nucleus are not what we say. They're non-relativistic particles. So maybe we can just treat them just as we treat other objects that go at less than light speed. Okay, neat.